I want to go over two examples from the book to illustrate the strategy for related rates problems. So it's going to be exactly examples in the book, but just glossed a little bit more precisely. And I'm going to illustrate the version of the strategy that I have written down that I posted on the Moodle and gave to everybody. The first thing for almost all these is draw a diagram. That's not because it's an absolute universal thing, but these problems are usually set up so that the key equations, like the master equation, things like that, are usually geometric. They're not always, but most of them are. And so you're going to have to draw a diagram to illustrate that. Okay. So here's the example 3, which we're going to start out with. And there's a water tank, and you see they draw the picture of the water tank. The second step, let me zoom out a little bit so you can see the whole thing pretty much. The second step is to label the diagram, and you've got to label the diagram with variables. Don't put in the constants too early. Only put in a number for something on the diagram if the quantity is truly a constant. So what they've got here is a pretty good diagram where they've got the water in this tank is at height h, and that's something that can change. And we're just going to put that in as h. And the radius of the top is going to be interesting to us too, because we're going to want the volume. That is also something that can change over time, so that has to be a letter. Now, the total size of the tank, the metal or whatever it's made of, those are constants. That's 4 and that's 2. And so you can put those in as numbers. But you don't want to put in the h and r as numbers too soon. We will know what they are at the end of the problem, but we don't want to put those in too soon. Now, the third step, this is very like their strategy, but I just make it a little bit more explicit. Express the given information and the desired rate in terms of derivatives of the quantities you identified in step 2, and watch out carefully for signs. Now, so let's read what they have here. It says that water is being pumped into the tank at a rate of 2 cubic meters per minute. So that's the rate of change of what? It's the rate of change of a volume. The units are a good hint for that. That's meters cubed per minute. It's the rate of change of something that it's in meters cubed with respect to time. So, in fact, we need the volume. That actually wasn't yet indicated explicitly on our picture, and we don't really need to label it on our picture, but it's going to be a crucial quantity. So, here's the way they say it. We're given that dV dt is 2 meters cubed per minute. We can put that in as a constant. If they give you actual rates, you can put those in as numbers. Okay. So, and it's being pumped into the tank, so that is positive. And what do we want to find? Okay, let's go back to the statement of the problem. Find the rate of change, find the rate at which the water level is rising. So, in terms of our picture, that is the rate of change of a quantity that we've already got on the picture. That's the rate of change of h. And so we're asking for dH dt. So this is the usual start of a related rates problem. We were given one rate, we want to find another rate. Okay? So that's done with step 3. And now step 4, as you can tell, it's the key step in a lot of ways. We need a master equation. And this is a little bit more complicated than what we did in class so far. There are more than 2 quantities here. There's V, which is the thing that we're told the rate of. There's H, which we want the rate of, but then there's this R quantity. We know that if we're going to relate V and R, we're going to have to use the 1/3 pi r squared h formula for a cone. And that's what they put in here. Okay? So, we've got this extra quantity. There are 2 different situations there, and I'll illustrate the other situation, we're talking about example 4 in a minute. But here's the situation where they do not give us the rate of change of R independently. They just give us dV dt and they want dH dt. So if there's 3 quantities, like in this problem, and you only are given one of the rates of change, you need to find some other relationship between those quantities to get it down so that it only mentions 2 quantities, the one that you're interested in and the one rate they gave you. And I usually call that an auxiliary equation. So that's what this stuff is in A through D here. If there are 3 variables and only one rate is given, you'll need to find an auxiliary equation. This often comes from geometry, e.g. from similar triangles. Well, that's what it comes from here. That's in fact what I'm thinking of, is this kind of example. Similar triangles is on my top 10, probably my top 5 list of simple facts that everybody's learned at this stage and that nobody really has a problem doing so much as people just have a problem remembering it. But it's a really, really important thing about triangles. And what we've got here is that R and H are linked together. And one way to see that similar triangles come up, even if you don't see it right immediately out of the picture, is just think about, why are R and H linked together? Or are they at all linked together? They better be to get an auxiliary equation. If the height gets larger, does the radius necessarily get larger? Yeah. The thing just grows proportionally. And if you think the word proportional, oh wait, how do I nail it down exactly what the proportion is? Similar triangles. This triangle with H and R is similar to this triangle with 4 and 2. That's where they're getting this equation. R over H is 2 over 4. And you use that to eliminate the variable that you are not interested in. Solve for the variable you aren't interested in terms of the one you are. Then they plug that in, and they get a relationship only between V and H. I call that the new master equation. So now we're ready to differentiate that master equation. Remember, the chain rule always comes in when you're differentiating that. These are derivatives with respect to t. Even though t doesn't appear explicitly in the equation, these are really, v is really a function of t, and it's a mystery function of t. And in fact, we won't ever know or care what the formula for v of t is. And we don't know or care what the formula for h of t is. That's the beauty of this method. We don't need to know, and we won't know. But we know some information about the rate of change of v and the rate of change of h, but with respect to t. So we're differentiating both sides. And this is just dv dt. That's all we can say. Luckily, that's a quantity that we know. And this is a function. H is a function of t, even though it doesn't look like it because it's just one single letter, inside another function, namely the cube function. So the pi over 12 hangs out in front. Then a 3h squared comes down, combines to make a pi over 4, and times the chain rule factor, which is dh dt. Then they solve for dh dt in terms of these quantities. And let's see, do we know h? Yes. They actually have said that, and we've purposely postponed even using that information. They say find the rate of change at which the water level is rising when the water is 3 meters deep. And that 3 is the thing we didn't put into the picture instead of h. We put in h because it's a variable, but now, after differentiating, we can put in the values of the variables. That's what I put in here, is that in 6 and 7, look carefully at units if you haven't already, and once you've taken the derivative, only after you take the derivative, and check the units, then plug in values for all the known rates and quantities. So you plug in the dv dt, you plug in the h, and you get your dh dt. It's positive, so that's implying that the rate of change is, that the height of the water is increasing. That makes sense because you're pumping water into the tank. Usually for these problems, you should be able to do a reality check at that point, that if you're pumping water in, V is increasing and H is increasing. And if you had gotten a negative number here, that would have been a worry. Sometimes when things are complicated and there's more than two things varying, that can be a confusion. Okay, so that's an illustration of either of their strategy, which is a little bit more concise, or mine, which kind of lays out some of these issues a little bit more explicitly and some of the pitfalls. Okay, so in the next video, I'll take a brief look at example 4 and just talk about how that's a little bit different. So I'll break here.